This is a short presentation of a new theory of flight presented to AIAA. A new theory is needed because the old theory is insufficient, as evidenced in a recent article in New York Times under the headline "Staying Aloft: What Keeps Planes in the Air?" with a frightening message. To those who fear flying, it is probably disconcerting that physicists and aeronautical engineers still passionately debate the fundamental issue underlying this endeavor. What is needed is to explain the miracle of flight, which is how it is possible for the wings of an airplane to generate lift balancing gravity at the price of drag or resistance to motion through air balanced by the thrust from the engines, with a lift-to-drag ratio L/D at least 10, of size 20 for an Airbus and up to 70 for a good glider, which means that it can glide 70 meters upon losing 1 meter in altitude. A wing is an airfoil which generates lift as it moves horizontally through still air, here from right to left, with then the flow of air around the airfoil from left to right. Here is a section of a typical wing with a rounded leading edge to the left, where the incoming horizontal flow attaches to the surface of the wing, and the trailing edge to the right where the flow separates. The airfoil is tilted with a certain angle of attack, which makes the flow unsymmetrical. Here is what you can see in a wind tunnel test, displaying the streamlines around a section of a wing under increasing angle of attack until stall. We see the flow attaching at the leading edge, staying attached on the upper surface, and leaving the trailing edge smoothly before stall. This is the flow we seek to understand, which means understanding the mathematics of the fluid mechanics. We shall see that the display of this experiment hides the secrets of flight. It is there, but you cannot see it. Here we see the forces acting on the surface of the wing with red high pressure and low pressure or suction under varying angle of attack, with the pressure rise and drop, peaking at the leading edge and dropping to zero at the background pressure at the trailing edge. We see separately the vertical lift forces and horizontal drag forces, with total lift much bigger than drag. We also see leading edge suction, helping to keep the drag small. Again, the 2D picture does not reveal the 3D secret to which we now turn. This picture reveals the mechanism of the miracle of flight, consisting of 3 components. The first one is attachment of the flow at the leading edge under pressure rise, indicated in red, which generates drag. The second one is pressure drop or suction on the upper surface, indicated in blue, peaking on top of the leading edge and then dropping to zero suction at the trailing edge. The suction generates lift. The third one is separation at the trailing edge without pressure rise or drop. Altogether, the blue area of lift is more than 10 times the red area of drag, resulting in an L/D bigger than 10. The first 2 components will be understood from understanding classical potential flow as a simple, understandable form of flow satisfying Bernoulli's law, while the third is the critical new element of the new theory, referred to as 3D non-potential rotational separation, or in short, elegant separation, as it reminds of the swirling departure gesture practiced in royal courts. We shall understand the flow around a wing by first understanding the flow around a circular cylinder, with the wing sharing the leading edge with the frontal half of the cylinder and the trailing edge with the rear half of the cylinder. One can also think of a wing as a sort of half cylinder generating lift. We note that the real wing has a smoothly rounded trailing edge and not the sharp trailing edge required by the circulation theory of lift by Kutta and Zhukovsky as the most advanced theory presented in textbooks, which we refer to as the old theory. The fact that the trailing edge is rounded is an important aspect of the new theory. We now start our analysis by considering potential flow around a circular cylinder as stationary, incompressible, inviscid, irrotational, that is non-swirling flow, which is a possible flow of air at speeds well below the speed of sound of relevance for birds, propeller planes and jet planes at start and landing. We see here a section through potential flow around a circular cylinder with high pressure in red at the attachment in the front, low pressure on top and bottom, and equal high pressure at the separation in the back, resulting in zero drag and zero lift. The flow satisfies Bernoulli's law with high velocity on top and bottom, where the pressure is low, and low velocity at stagnation in the front and back, with high pressure. The maximal suction on top turns out to be 3 times as big as the high pressure in the front, with a total lift on top about 10 times the drag by frontal pressure. We shall see that this is the desired L of D of size 10. But zero drag of a circular cylinder is not what is observed, and so there is something seriously wrong about potential flow, referred to as D'Alembert's paradox, formulated in 1752. The paradox was not solved until 2008, and when solved, revealed the secret of flight, as we shall now see. The real flow around a circular cylinder is potential flow at attachment and all the way around the cylinder until separation in the back, where the flow is no longer potential, with separation at high pressure, but instead non-potential, with 3D rotational separation without pressure rise or drop, that is, with elegant separation, thus with drag from the high pressure in the front. In short, rear flow is potential flow modified by 3D rotational separation. The 3D rotational or elegant separation comes from an instability of the opposing flows from above and below meeting in the back, which generate an oscillating velocity with pushes of air up and down as illustrated in the picture. On the other hand, the attachment is stable because the flow is retarded by the surface of the body and not by opposing flow. The oscillating velocity generates rotating flow with an oscillating pressure with zero mean, replacing the high pressure of potential flow. This is 3D rotational separation as elegant separation without pressure rise or drop, established by counter-rotating rolls of swirling flow attaching to the back of the cylinder, thus forming a flow with drag from absence of the high pressure of zero drag potential flow. This is the resolution of D'Alembert's paradox by Hoffman and Johnson from 2008. Potential flow modified by 3D separation arising from a basic instability mechanism of opposing flow. In this clip, we see a section of a 3D computational simulation of the flow around a circular cylinder, starting from rest, first quickly establishing potential flow with high pressure in the back, and by instability developing into a flow with 3D rotational separation without pressure rise, and thus drag. Here we see the same thing viewed from above with the rolls of rotating flow attaching to the back of the cylinder, clearly visible. Here we see the array of counter-rotating rolls of swirling flow developing from the back surface of the cylinder as seen from a point further downstream. From computational simulation, solving the Navier-Stokes equations with a slip boundary condition, making it possible to resolve the main features of the flow of importance to lift and drag. We can now rationalize the picture we started out with as potential flow modified by 3D rotational separation at a rounded trailing edge, with suction on the upper surface peaking at the leading edge and dropping to zero at the trailing edge, thus generating lift at least 10 times bigger than the net drag from the high pressure at the leading edge. This is the secret of flight revealed by computation. Understanding now the basic mechanism of flight, we are ready to analyze computational simulation of the wind tunnel test we started out with. We see here a section of computed 3D flow around the wing under increasing angle of attack, with the wing here kept horizontal and the wind changing direction. First pressure and then velocity up to and beyond stall. We see here plots of computed velocity left and pressure right for an increasing angle of attack from 4 degrees to stall at 17 and beyond to 20. We see the 3D rotational separation at the trailing edge before stall and at stall separation on the upper surface before the trailing edge. Comparing the computed pressure distribution on the upper surface as the blue curve and the high pressure below as the green curve with the leading edge to the left, we see very good correspondence with the dots representing measured values. In conclusion, we have discovered the secret of flight by computational solution of the Navier-Stokes equations, which reveal a mechanism of 3D rotational separation, which has been hidden to inspection. Finally, we compare the new theory with the old Kutta-Żuchowski theory, which modifies zero lift and drag potential flow, shown here, with large-scale rotation around the wing section, which is a mechanism for which the physics is missing. The Kutta-Żuchowski theory is thus an unphysical theory which does not describe real physics, whereas the new theory is a physical theory which describes actual, real physics.